this problem we have a charge of positive 5 nanocoulombs is placed at the origin, and another charge of positive 7 nanocoulombs is placed at 1.5 meters from the origin. We want to find the point between these two charges where a charge of positive 3 nanocoulombs should be placed so that the net electric force on that 3 nanocoulomb charge is 0. So first thing we're going to do to visualize this, we're going to draw a picture. We have at the origin, so at 0 meters, we have a charge of positive 5 nanocoulombs. And then if we have, going by halves, so 1.5 meters, we have a positive 7 nanocoulomb charge as well. And we want to know where to place the positive 3 nanocoulomb charge to make everything in equilibrium on it. Because this has a smaller amount of force, we're actually going to place that third charge somewhere closer to that positive 5. So this positive 3 we expect to be somewhere a little bit closer to the 5 than it is to the 7. Next thing we do is we write down our givens. I'm going to label these as charge 5, which is 5 nanocoulombs. Nano means times 10 to the negative 9. I'll label charge 7 as positive 7 nanocoulombs, and I'll label here as charge 3 positive 3 nanocoulombs. We want to find this distance x. And the way we're going to do this is we're going to say that the force on charge 3 because of 5 is equal to the force on charge 3 because of 7. And so the way that we're going to notate this is we're saying that the force on charge 3 because of charge 5 is equal to the force on charge 3 because of charge 7. So this is not force 35 and force 37. The way that the notation reads is the force on 3 because of 5, and this is the force on 3 because of 7. So they're going to cancel each other out. Now my formula is to replace these forces. My electric force is K Q1 Q2 over R squared. So the force between 3 and 5 we have is K Q3 Q5, and the distance between 3 and 5 we label as X. The force between 3 and 7 we have K times Q3 times Q7. Now here's the problem. We cannot label this distance here as a new variable. We can only have this one variable in there that we don't know. So I don't want to label it as a new distance like y. Instead, the way I'm going to label this is the total, which is 1.5, minus this part here, x. So the extra distance here is the total, which is 1.5, minus this part here, which is x. That whole thing then is squared. Now what we notice here, if we look at our values, since we have a k on both sides, they actually cancel out. And notice that since we have a charge 3 on both sides, they actually cancel out as well. In other words, it doesn't matter what this charge is, we would place it at the same spot regardless. So if it's 3 nanocoulombs, if it's 12 nanocoulombs, if it's 5,000 coulombs, it doesn't matter, we would place it at the same spot. This reduces now to Q5 over x squared equals Q7 over the quantity 1.5 minus x squared. Now I'm going to rewrite this. I'm out of room here. So I'm going to go to a new page and rewrite that. Q5 over x squared equals Q7 over the quantity 1.5 minus x squared. Now I'm going to cross multiply here. So I'm going to multiply x and Q7, x squared and Q7. I'm going to multiply 1.5 minus x squared and Q5. And so here I have, I'm going to just write 5 instead because it's 5 nanocoulombs times 1.5 minus x, the quantity squared. And then here, this is 7 nanocoulombs, so I'm just going to write 7. Now, I didn't convert either of these to regular coulombs because as long as I'm consistent on both sides, the units would cancel out anyway. So as long as this is nanocoulombs and this is nanocoulombs, I don't have to worry about my conversions. The next thing I'm going to do here is I'm going to divide by 5 on each side. So I'm going to divide this side by 5 and this side by 5. Here they cancel out. And I'm left with the quantity 1.5 minus x squared is equal to 7/5 times x squared. The next thing I'm going to do is I want to get rid of these squares, so I'm going to take the square root of both sides. Now on this side, when I take the square root, it simply gets rid of the square, and I'm left with 1.5 minus x. On this side here, I have the square root of 7/5, and when I take the square root of x squared, I'm left with simply x. The parentheses are really no longer necessary, so I'm going to get rid of those. And the next step is I'm going to add the x to the other side. Here they cancel out. This leaves me with 1.5 equals the square root of 7/5 x plus x. Now because both of these have x in them, this is kind of like a coefficient of 1, I can add 1 and 7 to the square root of 7/5. And when I do that, this side I still have 1.5, I get 2.18 times x. So if I add the square root of 7/5 plus 1, I get 2.18, and I still have the x on it. Now again, the reason I can do that is because both of them have the same variable x attached to them. My final step is I'm going to divide each side by 2.18. This now leaves me with an answer that x is 0.687 meters. So if I go back to my original diagram, I'm going to place this at 0.687, which again, notice that that is closer to the 5 than it is to the 7. Because this is a smaller charge, we have to place it closer to that to compensate.